marching men and weapons to the battlefront. Backed up by an aroused American nation, our air power grows mightier by the hour. With speed, born of long experience and inventive genius, raw materials dug from the earth become swift flying wings overnight. Millions of precision parts made of steel, aluminum, and other vital metals become giant engines ready to fly. Black crude oil raised from deep in the earth is transformed by the magic of chemistry into high-octane fuels to give these engines surging life, power, and speed. The petroleum industry is proud of its part in this mighty battle of the skyways, for from its long years of research have come the improvements in aviation gasoline which allow that fly our planes. From new refining units, skyscrapers of steel rising swiftly all over the land, comes a vast and ever-increasing flow of high-octane aviation gasoline. Great tanker fleets move endlessly across the 7 seas to give the United Nations air supremacy in every corner of the globe. Yes, oil is ammunition, for without it, these mighty wings cannot fly. But oil does not fly by itself. It takes men to use this ammunition, men who know how to use it. And while our boys make the best pilots in the world, learning to use it is no easy job. It means hard work, drill, and study. Such power cannot be handled overnight. It must be mastered step by step, as all you men well know. Remember the very first time you climbed into the cockpit of a training plane? That was your introduction to this new kind of power. Yes, of course, there were only a few horses in the nose of that first plane, but it seemed like a million, and you got a bang out of feeling that power respond when you revved her up. But bigger still was that great moment, that day when your instructor climbed out of that plane and said, "Okay, kid, take her away. She's all yours." Yes, that was the moment you'd been working for. That was one takeoff you'll never forget. For the first time, all the power in that roaring engine depended on your control. You were on your own, alone in the sky. Why, say you'd have tackled a Zero or a Messerschmitt right then and there. And then remember that first perfect landing you made all by yourself? Yes, you probably felt you were handling a lot of power even in that first trainer, and you wondered what it was going to be like to fly something really hot later on. That wasn't all you wanted to know about power either. For instance, why did they fuel your primary trainer with gasoline from a truck marked 73 octane, while over there a truck marked 91 octane was filling the tanks of a more powerful, advanced trainer? Why couldn't they use the same fuel in combat? Why do they have to be so careful to fill a fighter's tanks with 100-octane gasoline? What would happen if those fellows made a mistake and put this 100-octane gas into the tanks of a small trainer that called for 73? Or what would happen if you tried to use 73 octane in the engines of a flying fortress? That strange word, octane. What does it mean? Something to do with power, obviously, but exactly what? These questions are important. Knowing the answers may someday save your life or your plane. Maybe you've never realized it, but the gasoline we handle so casually every day is one of the most powerful substances known to man, far more powerful than the most destructive explosives. For comparison, we all know that dynamite has terrific energy. Far more powerful than dynamite is TNT, the king of war explosives, used in all our shells and bombs. Yet gasoline, the gasoline that carries those bombs to their target, has, pound for pound, 3 times the energy of TNT, 10 times the energy of dynamite. And if this tremendous power in gasoline is not kept under control, it can be just as destructive as dynamite. Even a little of that energy, running wild, can ruin an engine as efficiently as an enemy shell, and almost as quickly. To understand why, we must know what happens to gasoline inside an engine. Let's begin with a simple demonstration of gasoline combustion. Here we have an ordinary glass bottle. To close the bottle, we have a cork which fits tightly into the neck. Through this cork extend two wires connected to a spark coil so that a spark may be fired between the ends. To make our demonstration, we'll take a few drops of ordinary gasoline and squirt them into the bottle. Then with the cork, we'll close the bottle tightly. The gasoline, vaporizing and mixing with the air in the bottle, forms a highly combustible mixture. Watch closely what happens when a spark ignites this mixture of gasoline and air. This illustrates very simply the basic principle of gasoline combustion. The burning mixture converted the gasoline's energy into heat. That heat, expanding the gases in the bottle, created pressure. And the pressure blew the cork out of the bottle, changing the heat energy into mechanical energy. Now if we take this same glass bottle, turn it upside down, make it of steel instead of glass, expand the mouth to make a straight-walled cylinder, enlarge the cork into a close-fitting piston, put in a spark plug instead of wires, add manifolds and valves to admit fresh mixture and release the burned gases, then attach our piston to a central crankshaft, we have made our bottle into one cylinder of a typical aviation engine. This fundamental principle is the same whether it's applied to the smallest type of four-cylinder engine of a training plane or to the big engines that power a giant cargo carrier. But why is it that gasoline develops so much more power in one of these engines than it does in the other? Size alone is not the answer. Going back again to our bottle and cylinder, notice that there's a very important difference between the mixture we burned in our bottle and the mixture burned in the combustion chamber of an engine. The mixture in the bottle was under atmospheric pressure, the same pressure as the air outside. In burning, it develops very little power. But the mixture drawn into the cylinder is tightly squeezed by the piston to a small part of its original volume. This compression will produce far greater power from exactly the same amount of mixture. The measure of how much the mixture is compressed is called the compression ratio. For instance, if the piston squeezes the mixture to a fifth of its original volume, we say the cylinder has a compression ratio of 5 to 1. If it is squeezed still further, say to an eighth of its original volume, we say it has a compression ratio of 8 to 1. And in an engine of any given size, the more the mixture can be compressed by increasing the compression ratio and also by boost or supercharging, the more power each cylinder will develop. Higher compression has made possible the great increase in power of our modern engines without a proportionate increase in their size and weight. In theory, we could get still more power by carrying the compression higher and higher. But we reach a definite limit when we continue to raise compression in trying to get this added power. This limit is in the gasoline itself and is known as detonation, or more commonly, knocking. To understand what detonation is, let's take a look inside one cylinder of an engine and watch the gasoline mixture burn, slowed down several thousand times so that we can follow clearly exactly what happens. During normal combustion, the piston is just approaching the top dead center when the spark plugs fire. The instant that the sparks ignite the mixture, it starts to burn smoothly and evenly. Beginning at the points of ignition, the flame burns through the combustion chamber, advancing like a ripple when a pebble is dropped into a mill pond. This results in a steady push against the piston that delivers all the power of the expanding gas to the crankshaft. What you see here illustrates normal controlled combustion, the correct grade of fuel burning under normal operating conditions. In an actual engine, this burning takes place in a fraction of a second and is repeated hundreds of times a minute in each cylinder, producing in effect a continuous flow of power to the propeller. But it's a far different story when an engine begins knocking, as you will see now. Suppose that we are using a fuel that is not of the correct grade, a fuel of lower octane number than the engine is designed to use. When this lower grade of fuel is ignited, it starts to burn in a normal way. But let's stop the action for a moment at this point and see what is happening. The burning mixture, expanding and pressing toward the center of the combustion chamber from both sides, quickly shoots up the pressure of the unburned mixture here to an extreme degree, at the same time rapidly raising its temperature. Now, any inflammable gas has a certain temperature at which it will ignite of its own accord, and this unburned portion of the mixture quickly reaches its own self-ignition temperature. When that temperature is reached, this unburned mixture ignites of its own accord, and being under extreme compression, it suddenly explodes or detonates with an almost instantaneous white-hot flame of tremendous violence, like this. The shattering force of this detonation is what produces the characteristic metallic ting called knocking, and it is caused by using a fuel too low in octane or anti-knock quality to withstand the high compression built up in the combustion chamber. In an automobile engine, this knocking isn't so serious. Often you can hear it. But in an aviation engine, it can rarely be heard above the propeller and exhaust noise and is vastly more dangerous and destructive. These detonations, or super explosions, occurring hundreds of times a minute, release the energy in the gasoline so suddenly that much of it cannot be transmitted to the crankshaft as useful power. Thus, instead of getting full power from our fuel, we are now getting intense heat, wasted heat energy. The engine and cooling system cannot carry away all this excessive heat. The result is extreme overheating in the cylinder. In the engine test laboratory, we can show how quickly this extremely dangerous temperature rise takes place. Here we have a small one-cylinder engine running on a high-octane fuel. We're going to make this engine knock by simply switching to a lower-octane fuel, but first we'll mark the instruments at their points of normal operation. Head temperature, you can see, is now running about 450 degrees Fahrenheit, which is normal for this particular engine. Revolutions per minute are running a little over 1,300, which is also normal. At this speed, the engine's power output, which we'll also mark, is about 9/10 of 1 horsepower. The engine is operating on the proper grade of high-octane fuel, hence combustion is normal. There's no knock in the cylinder. But now we'll make our switch to a lower octane fuel and see what happens. Listen to the engine. Now watch the temperature. On low-octane fuel, the engine started to knock almost immediately, and within a few moments, under detonating conditions, the cylinder head temperature climbs from 450 to around 750 degrees. Note that this harmful rise in temperature is accompanied by a drop in speed of more than 400 revolutions per minute, a third of normal speed. And at the same time, note that our power has fallen off to less than 1/4 normal output. This shows clearly that with detonation, more fuel energy goes into waste heat, and less of it is converted into useful power. And that's just what happens in your plane engine if detonation takes place. In an aviation engine, such a knocking condition, if allowed to continue for only a short time, can crack or burn a piston or even blow a cylinder head, instantly putting the engine out of commission and possibly creating a life and death emergency for the pilot. Or at least a badly needed plane grounded for an overhaul or a new engine. Now that we know how important detonation is, let's answer some questions about octane number. First of all, what does it mean? Octane number is simply a measure of a fuel's resistance to detonation under compression. The more compression the fuel can take without knocking, the higher octane rating it gets. For example, 60 octane resists knocking under higher compression than 50 octane. 70 octane is better than 60, and so on. The higher the octane fuel we can provide, the more compression engineers can build into their engines. Thus, the greater the power those engines can deliver without detonation under normal operation. Every aviation engine is built to operate on a certain specified octane number fuel, and fuel of that specified minimum octane number must be used to prevent detonation. If the fuel used has too low an octane number for the compression of the engine, detonation will result. For instance, if 73 octane were used to fuel a flying fortress, that big bomber probably could never get off the ground. If it did succeed in taking off, its engines would be badly damaged. But you can also remember this. There is no danger whatever in using a higher octane than the engine calls for. As long as the fuel is better than the specified minimum, it is perfectly safe to use when the correct specification fuel is temporarily unavailable. But just being sure you have the specified fuel in your tank is really only the beginning. There are also operating factors controlled by the pilot which can cause detonation in any engine, even though it is run on the correct octane number. These factors are temperature, pressure, and mixture ratio. The importance of these three factors can be shown clearly by using a typical aviation engine anchored firmly to a test block in the laboratory. Here we can show detonation in a way which we could not do safely in actual flight. This engine has the same kind of controls and instruments usually found in the cockpit of a high-powered plane. And in addition, a special laboratory instrument, a knock meter, which will instantly detect detonation when and if it occurs. Right now, our engine is running normally on the correct octane number fuel. Temperature is still low. This gauge is extremely important, for it tells us the temperature of the cylinder head, the spot where detonation occurs. A green line on the gauge indicates cruising range, the normal range of temperature for cruising, while a red line shows maximum takeoff temperature considered safe for this engine. Any temperature reading above this line means danger, for it can easily lead to destructive detonation. To prove this danger, we'll let our engine run until the cylinder heads are badly overheated. Our temperature is now dangerously high, but with the engine idling, there is still no detonation taking place as the knock meter shows. But what would happen if we tried to use the maximum allowable power of this overheated engine? On a takeoff, for instance. To find out, let's pretend we are on a takeoff and see what happens. So far, okay. There she goes. Within a few seconds, our knock meter begins to register. The instant the detonation starts, our temperature begins to climb still higher. In the short length of time which would be required for a takeoff, we've developed severe and dangerous detonation. A few more seconds of this, and our engine might easily be ruined. Better throttle back. Here in the test laboratory, knocking is easy to detect, but in an actual plane it might develop and the pilot never know it until too late. Prevention is the only cure. Don't allow your engine to become overheated before you take off. Remember, there are several possible causes of overheating that the pilot must watch. Such overheating may be caused by warming up for too long a period at too slow a propeller speed to give proper cooling, or by long idling with the ship pointed downwind, especially in hot weather when the ground temperature is high. Or it might easily be caused by making a long taxi downwind, particularly in summer or in a hot climate. So take warning. If you see your cylinder head temperature is too high before taking off, check your operating conditions immediately. Cowling flaps should be open. Any other cooling adjustments on your particular plane should be set for maximum cooling. The carburetor heater should be set full cold, unless you know from the temperature and humidity of the outside air that there is danger of carburetor icing. Mixture should be full rich, since a rich mixture burns cooler than a lean mixture, and thus tends to cool the combustion chambers. More about mixture later, but first, let's go back to our test stand and look at the next important operating factor that the pilot must watch to prevent detonation: pressure. Here is a simple drawing of a typical fuel induction system. Since the compression ratio is part of the engine's basic design, the pilot cannot change it to get more or less power. Instead, he changes the amount of mixture which enters the combustion chamber by opening or closing the throttle. The amount of mixture which enters the cylinder through the intake valve here is proportional to the pressure built up here in the intake manifold through which the mixture passes. Hence, the manifold pressure becomes a measure of the power that is being developed in the cylinder. It is extremely important for the pilot to know just what this manifold pressure is at any time. To give the pilot this information, a pressure line leads from this point in the intake manifold to a manifold pressure gauge on the instrument panel. On our test engine panel, we have a similar manifold pressure gauge. Actually, the power developed involves some other factors, such as engine speed. But for our present demonstration of detonation, we can assume a constant speed prop, which will maintain uniform RPM. A red mark on the gauge indicates the maximum takeoff pressure permissible for any particular engine, a pressure which can safely be used for only a very short period of time. The lower range of manifold pressure, indicated by a green line, is our cruising range, safe power output for continued use. Your manifold pressure should always be kept within this limit when cruising. Between these two lies an intermediate range used for prolonged climb or when extra power is needed in an emergency. On some gauges, this is shown by a yellow line. These manifold pressure readings should be treated by every pilot with the greatest respect. Driving an engine to excessive power output means you are building up too high a pressure in the combustion chamber, and such a condition will quickly cause detonation. Let's watch this and see for ourselves. With our engine cooled down again, let's try another takeoff, paying particular attention to manifold pressure. Our temperature is now safe for a takeoff, but we're going to draw more than the maximum allowable power output. All right, let her go. Okay, operation so far is normal. No knocking. Manifold pressure is safe. But now, let's open up a little more. There she goes. Detonation almost immediately. Let her throttle back. This shows clearly that using more than maximum allowable power is another sure way to get into trouble. Again, prevention is the cure. Never exceed the maximum allowable power output of your engine, unless extreme emergency demands it. Even then, the emergency must be carefully weighed against the possibility of engine failure. And now for the third important operating factor in controlling detonation, mixture ratio. On some planes, mixture ratio is controlled automatically. On others, the control is manual, as it is here on our test engine. A rich mixture is one containing a relatively large proportion of gasoline to air, while a mixture containing a proportionately small amount of gasoline is called lean. On our panel, we have an exhaust gas analyzer, which enables us to tell what ratio of gasoline to air is being burned in the engine. This information is particularly important on the test stand, where the safe operating conditions of various engines are established. Under high power output, a rich mixture burns cooler than a lean mixture. Thus, rich mixture tends to prevent overheating and detonation when maximum allowable power is being drawn from the engine, and must always be used for takeoff or at any other time when maximum power is required. A lean mixture, on the other hand, is much more economical since it uses less fuel and is therefore used for normal cruising at higher altitudes to increase economy and cruising radius. However, leaning the mixture too much will cause a drop in power and delayed combustion, which may tend to overheat and burn the exhaust valve. Thus, too lean a mixture, indicated by backfiring or excessive cylinder temperature, must also be avoided. The importance of proper mixture in preventing detonation can be shown easily here on our test engine. Again, let's simulate takeoff conditions. This time with our cylinder head temperature well down, but with our mixture lean instead of full or auto-rich, as we know it should be when maximum allowable power is to be used. All right, pour on the coal and let's see what happens. Within the few seconds that it would take a plane to get up to speed for a takeoff, our engine begins to develop detonation, which continues to grow worse. This condition is definitely dangerous, as shown by the rapidly rising temperature. Before this condition gets out of hand, let's quickly apply the remedy, a full or auto-rich mixture. Within a few seconds, the character of combustion changes completely and detonation disappears. Remember that in all of these demonstrations, this test engine has been running on fuel of the specified octane number. Yet even with this fuel, improper operation of the engine has produced detonation, proving that the pilot himself has a big responsibility in preventing knocking even when the specified grade of fuel is used. Once in the cockpit, the pilot must be constantly on the alert from the instant that the engine is started. Temperature must be kept under control. As you warm up your engine, swing it into the wind if you're in a position to do so. Don't take unnecessary chances. If you have to make a long taxi downwind, especially in hot weather, keep an eye on your head temperature gauge. In addition to your ignition checks, be sure your prop is correctly set, that cowling flaps and all other adjustments are set for maximum cooling. Carburetor heat set for full cold, unless you know there is danger of carburetor icing. Mixture rich for cool combustion. Now, as you give her the gun, don't fail to make that vital 1, 2, 3 check. Temperature, normal. Manifold pressure, inside the line. Mixture ratio, rich. And you're off with no danger of a detonating engine. The rules are the same whether you're handling one engine, two engines, or four engines. And remember, use maximum power output for the shortest possible time. As soon as your plane is airborne, with landing field obstacles cleared, throttle back for your climb to altitude, thus reducing your manifold pressure. This position may be kept for climbing as long as your temperature remains within normal operating range. When you have reached an altitude where you're going to cruise, you can throttle back again to normal cruising manifold pressure. If you're making a long cruise at fairly high altitude, your mixer can now be leaned out for greater fuel economy and cruising radius without danger of overheating or knocking. In flight, constant check must be kept on all operating conditions. Abnormal operation, if not detected quickly, can develop trouble surprisingly fast. Cylinder head temperature should be watched closely. Power output should remain constant under uniform cruising conditions. Any abnormal, sudden, or unexplained rise in temperature at any time is a danger signal, a warning of conditions which may bring on detonation. The condition must be corrected immediately. Enrich your mixture. Reduce manifold pressure by throttling back until temperature comes under control. During combat, of course, anything can happen. Any part of the engine or cooling system may be damaged. Maximum power may be demanded, regardless of conditions. But even in the heat of battle, a good pilot will instinctively try to balance the needs of the emergency against the condition of his engine. For without an engine, the fight is over. And remember that the greater number of engine failures do not occur in combat, for actual fighting time is short. They occur during the thousands of hours of everyday flying, training, ferrying, patrolling, reaching the enemy, and getting back again. And remember, too, to fly and fight, the odds are yours. From production lines all over our country are coming the finest engines in the world for you to fly. From giant refineries flows an endless stream of the best fighting fuel in the world. High-octane gasoline our enemies cannot even hope to make in the quantity needed for this global war. Yes, you men have the power to win. It's up to you to make the most of it.